So our strategy seems to be alright, okay, everything seems to be fine. We just need to start with wave equation for Hz, but we already know what the wave equation for Hz, right? What is the wave equation for Hz? I have del square Hz minus omega square mu d epsilon d. This d stands for dielectric, okay, times Hz must be equal to 0. This of course works only in the dielectric film region or dielectric region in this particular case. The same equation will hold, except you replace this mu d and epsilon d by mu 0 and epsilon 0 for the case of, this must be plus, so this is plus, for the case of outside the dielectric region, okay. So these are my equations. From them I will have to write down this, I will have to solve Hz, okay. Del square of course consists of del square by del x square plus del square by del y square plus del square by del z square. I have no dependence on x, therefore the first term vanishes. I do not know the dependence on y, therefore the second term remains. I know the dependence on del square by del z square, which is basically minus beta square, right. So this is what I have. So this is minus beta square, and you can substitute this into the expression to obtain Hz both in the dielectric and outside the dielectric region. And because there is only one dependence on y, I can change this partial derivative of del by del y into the total derivative d by dy. I have d square Hz by dy square plus omega square mu d epsilon d minus beta square into Hz equal to 0. This is for the dielectric region. The same equation will be d square Hz by dy square plus omega square mu 0 epsilon 0 minus beta square times Hz is equal to 0. In these equations Hz is a function of y. We can have a shorthand notation, so call this omega square mu d and epsilon d as k y d square, and call this mu omega square mu 0 epsilon 0 minus beta square as k y 0 square, okay. The 0 stands for outside the dielectric region. Now how do I solve this equation? Well, these are second order ordinary differential equations. The solution for these equations is also known. Hz of y will be some a cos ky d y, or it could be sin ky d y. Now this is for the dielectric region, correct, and for the air region or outside the dielectric, the same equation will be some c cos ky 0 y. So let's, sorry, I made a small mistake here, so it must be ky d, not d coming in the numerator, it is just the subscript for ky, plus d sin ky 0 y. This is for the solution in air. So we have these solutions. Of course the dielectric region goes from minus d by 2 less than or equal to y less than or equal to d by 2. This would be y greater than d by 2 or y less than minus d by 2, right. So these are the dielectric and air regions that we have written down over here. I have now 4 unknowns a, b, c, d. I will have to apply boundary conditions to match them and see whether I am actually able to get anything over here. Now before we proceed, let us actually understand whether these equations the way we have written down are reasonably alright or not, okay. If you look at the top one, you wanted a propagating kind of a solution, right. So you wanted a cos ky y and a sin ky y type of a solution. However, in the air region we seem to have made a mistake. What is the mistake that we have made? We do not want a wave which is propagating along y. In fact, what we want is a wave which is decaying along y, right. So if you graphically look at this cos ky y, assuming that that is what I am looking at, so if this is my y equal to 0 axis, so cos ky y would be a wave which would go like that. If it was metallic wall, it would have gone down to 0 at both ends, but since this is not a metallic wall, there would be a small penetration of the wave here outside the dielectric region. Now once outside you are there, you do not want further, a sine or a cos kind of a solution. Although in some cases you are you will not have any control, and then you will have to accept this propagating solution, or sometimes you desire this. Okay, in cases where you want to couple light from one waveguide to another waveguide, you want a cosine kind of situation right outside the dielectric region of the first waveguide as well, but that is not our intention. We are not coupling anything from one to another. So for us, this inside the dielectric is perfectly fine, but outside the dielectric we want the wave to basically decay to 0. Okay, so we want the wave to essentially go down to 0 outside the dielectric region, which means that I cannot choose them to be propagating type of solutions, rather I have to choose them to be decaying kind of solution. So the solution here in the region above y equal to d by 2 we can choose this as C exponential. We want them to be decaying exponentially, and that would happen when beta square is actually greater than omega square mu 0 epsilon 0, but when beta is less than omega square mu d epsilon d, then you will have the propagation inside and decay outside. We will see that one in a moment. So C e to the power minus, call this as alpha and y. Okay, so I just need a decaying solution, I do not want an expanding solution, therefore I will take this as minus alpha y, but I know that at this point I do not want the expression for the decaying wave to be equal to C. I want this value to be valid at d by 2. So I just shift the origin from y equal to 0 to y equal to d by 2 and call this as e to the power minus alpha y minus d by 2, which would be valid for the region above the dielectric. Why? Because you put this y equal to d by 2, you get this expression exponential will be 1 and the value here will be equal to C. Okay. Similarly, for y less than minus d by 2, I shift the origin. Okay, I take this as e power plus alpha, because now the value of y is negative, so I take this as y plus d by 2. Okay, so now I have complete solutions for Hz except for the constant C and D, which I will now have to evaluate by applying boundary condition. These two are the solutions in air, one above the dielectric, one below the dielectric. This is the solution inside the dielectric region. Let us write down also what is this alpha. See, I have this d square Hz by dy square. The way I would solve this second order partial differential equation would be to push this ky square d outside. So I will have minus ky square d Hz, right. As long as ky d is greater than 0 or ky d square is greater than 0, the solution of this one will be Hz as cos of ky dy or sine of ky dy. Okay. So this would be the solution for Hz as long as ky d square is greater than 0. But what is ky d? Ky d is nothing but omega square mu 0 epsilon 0 mu r d epsilon d, right, minus beta square. This is my ky d square, the propagation constant inside the dielectric region. But I can write down this mu square mu 0 epsilon 0 as some k square, okay, inside air. This is the same thing that would be there in the air as well. So I can as well have a shorthand notation for this, and if I assume that mu r d is equal to 1, okay, that is the dielectric medium is in fact non-magnetic, then I can eliminate this mu r d from the discussion, and I also know that epsilon r d would be the refractive index of the dielectric region. Therefore I can consider this as nd square, okay, nd standing for refractive index of the medium. Okay, so I have k0 square nd square minus beta square. This is your propagation constant ky d inside the dielectric region, and this has to be greater than 0, which means that beta must be less than k0 nd. This is the first condition. Now to the same equation outside the dielectric, let us say above the dielectric, this should be equal to minus omega square mu 0 epsilon 0 minus beta square times Hz. Again, if omega square mu 0 epsilon 0, which can be written as k0 square, is greater than beta square, the solution will be of the form of cos and sine, which is what I do not want. So what I really want is that this k square, this fellow, should actually be less than 0, right. So if this is less than 0, then this would be negative, okay, so that I can have a exponential solution. Then I will have actual solution will be in the form of beta square minus omega square mu 0 epsilon 0 times Hz, and then that would be the solution. So what I will do is I will define alpha square as beta square minus omega square mu 0 epsilon 0 or beta square minus k0 square. Okay. So if this is my alpha, or rather we can define alpha as minus beta square minus k0 square. So if I define this way, then this is k0 square minus beta square, so this would actually be minus alpha square, so everything is alright. So if I define alpha square as beta square minus k0 square and then demand that alpha should be a positive quantity, the way it can happen is when beta is greater than k0. So I have two conditions for propagation, that beta must be greater than 0 but beta must be less than k0 nd. So if I were to plot the numbers, this is where the lower limit for beta would arise, that would be k0, this would be the higher limit k0 nd, and somewhere here will be the value of beta. You can actually combine these two equations and eliminate beta, but then you will be expressing everything in terms of alpha. Okay. So we now have the solutions for Hz, we know where the solutions would be and how the solution formats are, and all that we are going to do with boundary condition is to stitch them together at this point. Okay. So we apply boundary condition to stitch them together. What sort of boundary condition should we apply? Can I apply tangential Hz is going to 0 at the two boundaries? Unfortunately I cannot. This is a dielectric and a dielectric boundary, right? Well, in this particular case I can, but if you go to Ez I will not be able to do so. So I can actually try and apply the continuity condition. Moreover, the form of the solution indicates that this itself can be split up into two types. One is cos kyd and the other is sin kyd of y. This cos will be a symmetric waveguide with respect to the center. Okay. So this would be symmetric, or we can call this as even mode because the mode shape is essentially even. Okay. For the odd mode, which would be in the form of a sine wave, right. So it would be a sine, which means that if this is my axis, then this should be a sine. So it should actually go something like this. So this is how the sine waves should look, and they are actually odd in the sense that at the y equal to 0 plane they actually carry opposite signs, whereas the cos will have the same sign, and therefore that would look like a symmetric or even waveform. So let us look at odd waveforms first. Okay. So which means that my solution inside the dielectric will be of the form of sine. So I can write down Hzy for the odd TE case. I will leave the even TE case as an exercise for you. So for the odd TE case, Hz of y is equal to b sin kyd. Rather than calling this as b, let us simply call this as H0, that 0 nicely indicating that this is an odd TE mode that we are considering. So you have H0 sin kyd. For this one, the solution is valid for y less than mod y less than d by 2, that is inside the film. We can also find out what are the x and y components for this particular mode. So Ex of y will be equal to minus j omega mu 0 divided by ky or kyd times H0 cos ky y, okay, after applying the boundary conditions and then appropriately differentiating this Hz, because Ex will be proportional to del Hz by del x multiplied by some constants over here. Similarly, you can show that Hy of y will be equal to minus j beta divided by kyd H0 cos ky y. Okay. So these are the solutions for Ex and Hy. We also know the solution for Hz. Now we can actually apply the appropriate boundary conditions. We can write the equations for air region as well. So first consider y greater than d by 2, for which Ex of y becomes minus j omega mu 0, but the differential of Hz is now e power minus alpha, therefore it would be alpha that is coming out in the denominator. So that would be alpha H0 sin ky d by 2, that would be the at the boundary the continuity condition, e power minus alpha y minus d by 2. Okay. and then you will also have the solution for Hy, which is minus j beta divided by alpha H0 sin ky d by 2 e to the power minus alpha y minus d by 2. If you are slightly confused at this point, we can actually go back and apply the boundary condition. I assume that you could apply the boundary condition very nicely. So let's write down this as H0 sin. So this is how you apply the boundary condition. I am going to just motivate the boundary condition to you. I will not go into details for this one. Okay. So this is H0, right, sin ky dy. This was the solution as you would be there in the dielectric region. This at y equal to d by 2 must be equal to the condition for the wave at air, right. So at y equal to d by 2, if you approach from the top, the solution would be in the form of c e to the power minus alpha y minus d by 2. Therefore at y equal to d by 2, this would be equal to c. So this would be equal to c. So c is equal to H0 sin ky d by 2, and this is precisely what this factor is coming in over here. Okay, so this is the boundary condition, and this is the amplitude of the wave outside the dielectric region. Similarly, you have H0 sin ky d y at y equal to minus d by 2 must be equal to d, which is the amplitude at y equal to d by 2, right. So you y equal to minus d by 2, but if you substitute for this, sin becomes sin of ky d into d by minus d by 2 becomes minus H0 sin ky d by 2 is equal to d. Okay, and this is precisely what you get if you were to write down the expressions again for the region y less than or equal to minus d by 2. Okay. So once we have determined everything, and you can now clearly understand where H0 must be coming from. H0 comes from the total power normalization. What is the power that is actually carried by the wave, and that integral will tell you how to fix the value of H0. So we have figured out everything. We know how Hz looks like, we know how Ex looks like, you know how Hy looks like. Okay. We know that Hz as a function of y is a cosine wave, and depending on the order, so you can have m is equal to, the solutions will be of the form of different orders, right, because you have a cos ky d by 2, and you can approach the same value in two different waves. So you can approach it by 1 half cycle, you can approach it by 2 half cycles. Okay. So let me try to draw 2 half cycles over here, and this is how the wave would decay outside. Okay. So I need to approach it with a different or 2 half cycles. So let me try that. This is the second cos ky d by 2, or rather if we were to plot it in this way, this is my fundamental mode. The next mode will be this one, right. So it would actually approach in this way. So this is the next mode, and now I can draw the higher order modes if you want. This is the next higher order mode. Again, as I said, the drawing is slightly confusing for me, but these different modes correspond to the different orders. Again, there is no specific greatness about these mode orders. They just indicate the possible solutions as the different mode shapes contained by the electric and magnetic field component. They just come in different flavors in which a sustainable E and H patterns for the particular solution would exist. So these are called as modes. Let me close this discussion on dielectric waveguides. I mean, I have not written down the expressions here for y less than minus d by 2. I will leave that as an exercise for you. Okay. So you write down the expressions for y less than minus d by 2. The solution for even TE would not change. Okay. Sorry, I wrote down the expressions as even TE, but I was talking in terms of odd TE. So for the solution for even TE, there is no problem. Instead of sin ky d by ky dy, you will write down this as cos ky dy, and then you would simply continue applying the appropriate boundary condition. The crucial point here is that Hz was not equal to 0, but then the tangential Hz was simply continuous. You do the analysis for TM waves, and I will leave that as an exercise for you. Let us discuss one aspect, which is cutoff frequencies for these modes. So how do we define the cutoff frequencies? Well, when we have the propagation, right. So you start with alpha, you also know what is KYD, right. So alpha is basically given by writing down the boundary condition. You will be able to express the relationship between alpha and KYD, because I have, in one case I have H0 sin KYD by 2 and the other one will be a cos KYD by 2. So the ratio of alpha to KY can be written down as alpha by KYD is equal to tan KYD. So tan KYD d by 2, this can be obtained again from the boundary condition. This relationship tells you the different values of KYD and alpha. How do you choose them? Of course, solving this equation is kind of very difficult because KYD is present on both left hand side as well as on the right hand side. These equations are known as transcendental equation, and the solution of this has to be done by a numerical analysis. We will not go into those details in this particular case. Okay. So you can obtain this equation, as I said, from the boundary conditions. We will not pursue this one, but you can actually add alpha and alpha square and ky square. Okay. So I know what is KYD square. KYD square is nothing but k0 square n d square minus beta square. I also know what is alpha square. Alpha square is nothing but beta square minus k0 square. So if I add these two together, I get alpha square plus KYD square equal to k0 square nd square minus k0 square, or taking k0 square as a common factor, I get nd square minus 1. Okay. Now I can express what alpha is. Alpha in terms of KYD, that would be equal to k0 square nd square minus 1 minus KYD square. Remember, whenever you have KYD value which is non-zero, there will be a mode which is propagating. Okay. So this is your expression for alpha. What would happen to the phase constant beta, right? See, as alpha goes to 0, beta would simply approach k0. That is from this expression, very clear, right? So if alpha goes to 0, the way it can go to 0 is when beta approaches k0. So for a given k0, alpha will go to 0 because beta is approaching k0. So with that, let us actually, so when that happens, with alpha is equal to 0, the waves are no longer cut off, right? The waves are no longer bound to the dielectric region, and therefore the waves are cut off in the sense that they would not be confined inside the waveguide. Why? Because if the wave, if alpha goes to 0, then alpha times y minus d by 2 was the solution outside the dielectric region at the air for y greater than d by 2, but with alpha going to 0, the solution would not decay, but rather it would remain a constant. There was a c times e power minus alpha, and we also saw how to obtain c, but the point is that as alpha goes to 0, the c times e power minus alpha y minus d by 2 does not go to 0 as you increase y, rather it remains fixed at a given value of c, and therefore energy is carried away from the mode outside the air region. Similarly, if you go to the bottom surface or the substrate region, you can see the same condition. So alpha going to 0 implies modes are being cut off. Okay. So this is a situation where the waves are cutting off, and the solution for that would be to look at, since I know the relationship between alpha and KYD, as alpha goes to 0, the solution can only happen when KYD d by 2 would go to 0 or the integer multiples, right. So this should go to either 0 for tan to go to 0, or it should go to, so let us just write down this as multiple of pi, m standing for different orders, right. So with m is equal to 0, 1, 2 or 3, you will have different modes coming in. If you want, you can replace m pi by n minus 1 into pi and set n is equal to 1, 2 and 3 and so on. This is sometimes used. This m notation or n notation is used in literature, both are used. So either the first mode will be TE 0 mode or TE 1 mode. TE 1 mode would indicate a half cycle, TE 0 mode would indicate no minima in the region. Okay. So these are just kind of two different notations, but the essential idea is that these mode designations actually follow because they are getting multiples of pi and making this tan of this expression equal to 0. Okay, but I know what is KYD, right? I know what is KYD. I can write down the condition at which this happens by specifically writing this as omega CD by 2 square root of epsilon RD, which would be the expression for this one, minus 1. Why minus 1? Because epsilon R of air is equal to 1, and this epsilon RD is nothing but ND, epsilon RD under root is nothing but ND square. Okay, so this is the condition where we would have this one. So K0 square of course is omega square mu 0 epsilon 0. So I am basically using this expression for KYD square. When alpha is equal to 0, KYD square will be equal to omega square mu 0 epsilon 0 ND square minus 1, or KYD will be equal to omega square root mu 0 epsilon 0 and under root of ND square minus 1. So let us write down that. So it would actually be omega c, which is the cutoff frequency, square root mu 0 epsilon 0 divided by 2. There is also a d here, then there is square root of ND square minus 1. Okay. So this must be equal to n minus 1 into pi if you are going to this notation for the waves to be cutting off, or rather this expression must be equal to n minus 1 into pi. You can replace omega c by 2 pi fc, right, and divide by 2, 2 will cancel, pi will cancel from left hand side and the right hand side. So fc can be written as n minus 1, do not confuse n with refractive index, n minus 1 is the mode designation, divided by square root of mu 0 epsilon 0 d n d square minus 1 under root. But I know 1 by square root of mu 0 epsilon 0 is c. So I have c n minus 1 divided by d square root of n d square minus 1. So these are the cutoff frequencies for higher order modes. So with n is equal to 1, clearly fc is equal to 0, indicating that no cutoff for the fundamental mode. Okay, there will always be this particular mode that would exist. So there is no cutoff for fundamental mode. So for the odd modes, the cutoff condition is this one. This is for the condition for odd TE modes. Okay, what would be the cutoff condition for the even TE modes? You can actually show that instead of tan it would be cot. So I will not derive this one. So the cutoff condition for the even frequency modes will be equal to n minus half divided by d into square root of nd square minus 1. Okay, this minus half simply indicates a pi by 2 shift in the argument that needs to be used. But the important point is when n is equal to 1, fc is not 0, which means that first the odd TE mode will propagate the fundamental, then the even TE mode will propagate. Okay.